So picking up where we left off, what we want to do is kind of see more interpretation of our heat model, heat flow model. And that was U sub t equals alpha squared U sub xx. Now notice the reason alpha squared, why do a square? We'll see possibly later on that there are a couple of reasons to put a square on it. One is it tells you it's always positive. And so that's one thing to realize. Okay, so another way to interpret this is the model. So I write the model instead of it. The model indicates the heat profile is trying, as if it knew what it was doing, trying to straighten out between the temperatures at the two ends. Okay. So as we saw, as we kind of looked at possible graphical interpretation of what's going on, we had that end up as a straight line. So now, kind of where are we getting this? Okay, so let's just take some sort of curve like this, and let's look right here. So this is U of x and t. Now, down here, what I'm going to do is say that, we're going to move this way some h, or delta x, but I just like using h's. And so this point is u of x minus h and t. And if we come over here, this is u of x plus h and t. And if we look at their average of these two, their average will be at x, and it will be, that point on this straight line. So this is u of x minus h t plus u of x plus h and t divided by 2. So that's the average. And since, notice this is concave down, the heat is trying to go that way. It's decreasing, and it's heading toward that point. And, as soon as we reach that straight line, we'll see that basically that's saying, we've gotten a concavity of 0, right? And so nothing more is going to happen. Okay, so let's look at Taylor series to kind of see this a little better. Now I'm going to drop the t here at first and just look at one dimension. And, so suppose I want to look at some x0, which is x plus h. Okay, so I'm looking up to the right of things. Then, using Taylor series, I can write that u at x0 is equal to u at x plus u prime at x times h, that delta x or whatever, plus u double prime of x h squared over 2, and then plus other stuff, okay, the cube and the fourth and all that. So that we get that as that stuff. Now, if instead I said, well, let's let x0 equal x minus h, well, actually, yeah, I'll just leave it that way. Then u of x0 would equal u of x minus u prime of x times h. Now the reason the minus is you've got an x minus h in here, so that delta x is actually a negative h. And then plus, because we're squaring the h, u double prime of x over 2 h squared plus stuff. Not necessarily the exact same stuff as up there, but it's just a bunch of stuff. So now let's add these two, and we get 2 u at x0 is equal to, oh, sorry. Yeah, I messed that up. Yeah, I did want to, let me come back here and we'll call this one x2 and x1 here, because that's definitely not 2 there. Okay, so what we have then is our u of x2, which now I'm going to write as u of x plus h, plus u of x1, which I'm going to write as x minus h, because that's what those were. That's equal to 2 u of x. These cancel, and then plus u double prime of x, not over 2 because there's 2 of them, times h squared, plus a bunch of stuff. Okay, now if I solve for u double prime of x, you see I get u double prime of x, and I'm going to say is, excuse me, approximately equal, sneezing fit there, is approximately equal to the u of x plus h. Now I'll stick in here the minus 2u of x, and then the plus u of x minus h, all over h squared. And see, I got rid of the stuff, and that's why I'm using approximately equal to. And the smaller you make h, the better this approximation is. Okay, so there's the Taylor series part of it. Now I'll put t back in as a variable. And so instead of u double prime like this, I would write u xx of x and t is approximately equal to u of x plus h and t minus 2 u of x. Oops. Try that again. To u of x and t plus u of x minus h in t all over h squared. Okay, so now, we would write it like that. And so we're saying that concavity, that exact concavity is pretty close to this. And so again, we're looking at what was my original picture? I had concave down on that, so we'll do it that way. So here is u of x minus h in t. Here's u of x in t, and here's u of x plus h in t. Okay, so we have both of those. And now, if I write this just slightly differently, I'll factor out a 2 in the h squared. And so we'll have that our uxx, our concavity, it's some xt, is approximately equal to 2 over h squared. And what that leaves is u of x plus h in t plus u of x minus h in t, all divided by 2, and then minus u of x and t. And so here we can see it, so I factored the 2 out, which had me have a denominator of 2 on those side terms, and factored the h squared out of the bottom. And so if we look at it this way, then we can very much see that, one, if u of x and t here, over here on the right, is less than the average of its neighbors, okay, well then uxx of t is greater than 0, right? Because if the u here is less than this average, I'll get a positive number. And h squared is always a positive number. 2 is always a positive number. So then uxx of t is a positive number. And then by the model, u sub t is greater than 0. It increases, or u increases. Okay, 2, if they're equal, so u of x t is equal to the average of its neighbors, then uxx of t equals 0, and then u sub t equals 0. In other words, u doesn't change. And then finally, if ux of t is less than, what did I do here? Oh, sorry, I did less than. Is greater than the average of its neighbors. Then uxx of t, well, if is negative, because you see if this over here is the one on the right is the bigger number, then we'll get a negative, and so this will be negative, and so u sub t will be negative, or U decreases. Okay. And so that's a little bit fuller interpretation, plus using the, back here, using the Taylor series for numerical methods. This Taylor series approximation is a very important thing, and we'll see that a little bit later, maybe, as far as how that gets used for at least some types of numerical methods. Alrighty, so there you go. There's a little more insight into the model and how to interpret it. And now we'll move to things like boundary conditions and initial conditions.